Hello, everyone. Welcome to the SimScale webinar on multi-component analysis for food processing and packaging equipment. I'm Kanchan Garg, one of your presenters for the talk, and joining me today is my colleague Ajit Kumar. I'm a product manager here at SimScale, responsible for our product strategy and offerings in the industrial equipment and manufacturing segments. And Ajit is a senior application engineer with years of experience working on real-world engineering problems right alongside our customers. Hi, Ajit. I'm thrilled to be hosting another webinar with you. It's always a pleasure.
Thanks, Kanchan. Looking forward to the webinar.
All right. Actually, before we proceed, a quick reminder to you all that your mics are going to remain in mute. If you're facing any technical difficulty or if you have any questions, please feel free to use the questions or the chat options to get in touch with us. And so a quick look at how we are structuring today's talk is we'll of course start with a quick introduction to SimScale, not presuming that all of you know what SimScale is, who we are, what we do, and how we do it. And then we're going to look a little bit deeply into the food processing and packaging industry. We mainly want to share with you what we hear from our customers, and perhaps that will resonate with you as well. We want to look at various use cases within this industry where SimScale can be used. And specifically, we want to focus on our newly released gas mixing model, which is multi-component. And by way of showing this model, we'll also walk you through the different aspects of using the SimScale platform for running various kinds of simulations. And of course, we will make sure that we save ample time at the end to answer your questions. But you don't have to wait till the end. Please keep the questions coming. Please use the questions channel to keep posting your all your queries throughout the webinar. So what is SimScale? It is actually the world's first truly cloud native and fully SaaS simulation platform that has enabled engineers across the world to access simulation from anywhere, anytime, simply by having access to a web browser. You don't need any hardware, and there's absolutely no manual installations or upgrades that need to be taken care of, no VPNs required. Just simply open a web browser, log into SimScale, and start simulating. And under this unified platform that you see here, you'll find multiple physics ranging from fluid flow to structural analysis, as well as electromagnetics. And what we also allow is, because we are web-based, we are on the cloud, companies and teams have access to Google Doc style collaboration, which means that you can discuss your simulation projects, your designs, and how your overall project is progressing with your teammates, whether they are sitting in the next room or they are sitting across the globe. Everything can happen in real time within the platform. And you also have access to in-app support, where an actual real support engineer is available to help you with your simulations, answer your queries almost 24/7. And very recently, we also launched our AI-powered result prediction sitting right alongside our physics-based solvers. So because SimScale does all the heavy lifting in terms of your data management, your simulation results, all of this data is instantly available for training the AI model, which means that you can now use these models to predict how future designs might work. So what this allows is basically exploring a very vast design space, which is not possible until now, to narrow down and fine tune to that final design for which you may want to run the full physics model. Scalability, of course, is supported by almost the unlimited power of the cloud, which means that there is practically no limits on the size of the simulations, the number of parallel simulations you can run, or the data storage. All of this, the simulation process and data management, is taken care of by SimScale, so that you as an engineer, you as a team, as a company, can focus on leveraging simulation, leveraging physics-based analysis to fine-tune your product and innovate better products. Now, coming specifically to the food processing and manufacturing companies, here's where I want to share some of the things that we've been hearing from our customers, and perhaps this is a good opportunity for you to tell us if this resonates with you, if there are additional challenges that you would like us to also focus on. So, for example, the food processing by nature of the industry has to follow very stringent food safety and quality control regulations, all while keeping, staying competitive in the market and adhering to ever increasing steep net zero targets like reduce carbon emissions, improve energy efficiency of products. And of course, as an engineer, uh, working with your customers, you want to reduce downtime once the equipment or product is operationalized. And in case there is a failure, you would want to respond to it rapidly. So predictive design is becoming critical. And all in all, process and product optimization, doing it in a cost-effective manner, in an efficient manner, and by that I don't only mean product efficiency, but also engineering efficiency, efficiency of the team of a company to meet your targets in a timely manner is becoming critical. And what we have observed, what we have learned from experience is that organizations that will thrive competitively in such a scenario are ones that can rapidly iterate through design cycles through early, aggressive, and broad use of simulation, which is not supported by a traditional simulation stack uh, by legacy on-premise software. Because first of all, the simulation lead times itself are weeks, days, even months sometimes. All the simulation, different modules, different physics are scattered. You need a separate tool for different kind of physics. And the simulation knowledge is also very siloed, very concentrated within the expert team who are often overloaded with the work that they need to do. That is where SimScale as a cloud native simulation stack really has an advantage because, first of all, due to the unlimited compute power of the cloud, the simulation lead time itself comes down to hours and even seconds when you're talking about AI prediction. You have broad physics available sitting on top of best in class simulation methods, and all the HPC orchestration, user data management is taken care of by this cloud native platform, which basically means that as a company, as a manufacturer, as a team, you can focus on innovating faster, leveraging all these multi-physics solvers that are available to you. And as you can see here in the image on the right, that in terms of physics, SimScale offers structural fluid dynamics, thermal and electromagnetic solvers. But for today's webinar, we are specifically going, because of limitation of time, we are going to focus on the fluid dynamics aspect of it, where we will talk about our multi-purpose solver and specifically use one of our newly released features, which is the gas mixing model. But that is not to say that that is what SimScale is capable of. In fact, we will see in a while the different use cases within the food processing and manufacturing industry where you can use SimScale. A quick brief here about the multipurpose solver itself. It's a proprietary technology which is based on a finite volume RAN space solver backed by an automated, robust binary tree meshing. We'll also take a look at how one can go about setting up a simulation in this solver. And when we talk about the gas mixing model, it can be used for transport of multiple gaseous species within a mixture, accounting for the variation of density, viscosity, and thermal properties. And apart from using it within the food processing industry, there are other applications where this model can be used, which is like in an exhaust chimney, smoke dispersion, just mixers and tanks or pipes and valves. So I think this is also a good time for me to hand over to Ajit, who will talk about first. Okay, sorry, I forgot that we also have some testimony to share here, which I guess I'll just leave it for you to read through what our customers within the food processing and manufacturing industry talk about using SimScale, where they vouch that SimScale has helped them improve their conversations with potential customers, given them the confidence they need to present innovative designs while also increasing their product, the speed with which they are producing new designs and their response times, as well as time and cost savings. So we hope that this is something that you can relate with, and this is something that will spark curiosity in you to ask more questions about the tool. And with that, I'll actually hand over on this slide to Ajit, who will take you through broadly about what all SimScale can do for the food processing and manufacturing industry. And from there, he will also give you a live demonstration of the platform itself so that you can actually get a feel for what it would be like to use SimScale for your day-to-day engineering work. Over to you, Ajit.
Yep. Thanks a lot, Kanchan. As usual, you did a great job explaining how our customers use simulation in general to innovate faster and also troubleshoot customer-related cases. And in general, as Kanchan mentioned, I'm really excited to actually present in front of the audience on what we have in terms of the capabilities with multi-component gas mixing features. But let's take a step back and see through what are the other simulation modules that you can use to actually improve the components in a typical food preservation package and filling processing line, right? So as Kansan mentioned, this is not limited to a specific application area, but on screen, as you see, if you take a process line, there are multiple components that needs research and innovation. And also sometimes the aftermarket product troubleshooting can also come into play where you have tight deadlines to actually verify and also validate if your component is actually installed correctly, if at the place of installation, are they used in a way that the component is designed for? Those kind of questions can also be answered using simulation. In this case, on the screen, you see a typical preservative and packaging filling process line where it starts from a fluid pump, which is going to drive the entire flow within the system of ducting, within which you also have valves and flow control devices to actually increase the flow rate or control how much control the actual fluid flow through the system, right? With simulation, you should be able to break it down into single or different components and start analyzing or troubleshooting things. For example, you can run a pump analysis, which is required to actually drive the fluid through this entire processing line. So with SimScale, you should be able to quickly run parallel simulations, form a pressure curve or a pump curve, and then formulate the range in which this system should operate. On the other hand, you can also go into the storage side of things where you can do tank filling analysis, because in multi-component or preservative industry, the transport and also storage of these gas components are critical, right? Some gases are really volatile, and you need to take care if your storage facility is up to handling these gases while transporting or storage as well. So you can do sealing analysis to check if your systems are connected well, installed properly, so that if a gas flow happens, there's no leakage. You can also do pressure vessel analysis where you can find out if you're storing some volatile gas, whether it can withstand the pressure that is exerted by the gas itself to the storage facilities. If you go through the process line, there are other equipments which comes under the flow control devices like valves, where you can find out at which valve position or which valve um, opening you can actually achieve the required flow rate. And extremely on the flip side, if you have flow control system with electronic devices, SimScale can also be used to actually see the thermal effects and thermal cooling that might be required for some cases here. For today's case, we are trying to focus on one of the applications or one of the components here in the processing line, which is the mixing of multi-component gases. And in specific, we are going to look into a static mixer, which is typically used in food industry because of its easy to use, no movements or no moving parts. So they have a lot of advantages over the other kind of mixers as well. I'll make a pause here to remind the audience that you can already start putting your questions on the question section. So at the end of this session, we can pick them up and start answering them. Yeah. Let's dig deeper into the case study that we have today. So as I mentioned, it's going to be a static mixer. So on screen, you can see there are a few components of gas coming in, getting mixed due to these plates, and then we have an outlet that is coming out. Imagine we have a client that has come to us and say that, hey, we have an existing mixer component, but we want to actually see what happens if we need to improve the efficiency of the mixer, and what happens if you make design changes, and how does it affect how the component works in general. So A typical workflow in such a scenario will be like what you see on the screen. So either we should have we have a CAD engineer using the CAD tool to design the existing component. They can actually work together with an engineer to formulate what are the inputs, what are the outputs, what are the criteria for this product in specific, and then move these details to a simulation expert who can actually simulate this solution and then find any improvements or give the designer a feedback that, hey, this design doesn't work, so we need to change a few more parameters or change the plate design to make it more efficient or to actually customize it for a specific customer. What you can do with SimScale is, as Kanchan mentioned, we can cut down the communication time between a designer and simulation expert by enabling the designer or an engineer to actually simulate on few conceptual designs and then go to the simulation expert when the designer or engineer thinks that, hey, this design might be suitable for a prototyping or for a product release as well, right? So using SimScale, you can access the simulation even on your browser. So that gives the designer an additional level of uh, insight on what designs he or she is going to produce. And they can also verify quickly if the conceptual design they are thinking about is working or not, and then push it to the simulation expert at the validation level for prototyping and other purposes. And that's exactly what we are going to see today in a workflow for this static mixer. And to dive into the case, I'll quickly give a synopsis of what's given as an input. So we have the mixer with two inlets. So we have the nitrogen as a carrier gas. Because nitrogen is an inert gas, it actually tends to keep the environmental and conditions inert, right? And we have CO2 coming in into one of the inlets. That's going to preserve the food and inhibit the spoilage of fresh meat or fresh food, uh, which is going to be filled in with the preservative gases. We also have oxygen at a smaller level to actually make sure there is no respiration happening, but also to keep the products fresh as well. For an example, we are trying to actually fit this static mixer in a process line where the preservative mixing is required for fresh fruits. So you can see the ranges of the components that is required for this product and also the required filling rate here, right? Now imagine this as a project comes to a designer and the designer wants to actually do a small change to the plates available in the static mixer. So he or she is trying to add a few turbulent generators to see if this concept can increase the efficiency of the mixing, because creating turbulence will actually create a lot of space for the gases to mix before they pass on to the output. So that's just the conceptual design that we are going to test together using SimScale. And this is a good point where I can jump to the SimScale platform and show you how this can be done by a designer. Right? As you all know, SimScale is a cloud-native simulation tool. And if you want to get access to the simulations, all you need to do is go into simscale.com and then sign up for your account, where you can jump into the dashboard as you see here. Once when you're within your dashboard, you can start a new project. So I am putting on a hat of a designer who joined one of the food manufacturing company, equipment manufacturing company, without any CFD experience, right? So I have SimScale as my simulation tool, and I'm going to show you how I can start from scratch, use a design, simulate it, and then send it back to a simulation expert at the validation level. Yeah. So to start with, within the dashboard, you can create a new project. I'm going to say that it's a static mixer, and create. Once I am within my project, the first thing SimScale asks is to import a geometry. And as a new hire in the company, I'm not sure how to actually get the CAD for simulation, or I'm not sure how to set up a simulation. So in that case, what a designer can do is quickly create a simulation he or she can actually take a look at the templates that their simulation experts have already prepared and kept over the past years. So for example, here I'm looking into importing a simulation. I know that this is going to be a multi-component case, so I'm going into that folder. Now I have a template already prepared by my simulation expert. I'm going to pick that template and say, hey, I want to import everything that is related to this particular case for me to actually review, learn, and also start iterating on the design. So I'm going to import one of the simulations from the experts. I get a copy of whatever this simulation expert has done over the past few weeks or few years, which means this template is already verified by a simulation expert, where I don't need to actually go into each and every tiny detail before I can start iterating the design. This is such an advantage for any new users of simulation in general, and this enables even designers to quickly jump in and start some valuable simulation right away. Right? In this case, we have a simulation template. So we already have a geometry for the base case. If you look at the geometry in a transparent mode, we have flat plates, and we also have all the material properties set, the boundary conditions set, and I can directly go ahead and see how the base or existing case works by simply starting a simulation. Right? This is all a designer needs to do to actually know how the simulation works using a template. And as a next step, I want to actually make changes to the geometry, a slight change, and then see if the basic case is comparable with the new design and whether it improves my efficiency or it uh, it actually deteriorates the efficiency, or what is happening when I make the design change. To do that, I can quickly import a new geometry. So let's say I have one other geometry in my concept level. I'm going to import a version 2 and then say this is a parasolid file and import. And now I have a new geometry getting imported into my same project where I copied from the template. Once when the geometry is within the platform, all the designer needs to do is duplicate the template. So I get a copy of the basic template verified by my expert. I go into the geometry. I can swap the geometry, but let's take a look at the geometry of the new model here. I see that the model is a solid model, and for the simulation, we need a fluid domain, right? We want to capture how the fluid moves into the system and comes out. So to do that, I can edit this geometry and say, I need an internal flow volume. So SimScale provides these CAD editing options where you can have basic operations like editing a face, deleting, extruding, or doing a Boolean, or checking whether your model is good for simulation by um, looking at the interferences. And these operations can be done within SimScale itself. For this case, all I need is a fluid volume. So I'm selecting a seed face from where the fluid starts, and I'm capturing the boundary faces here on all the inlets and outlets. So these are the inlets. I can go to the outlet and select, hey, the fluid should end here, and I can apply. This will automatically create the fluid volume required for the simulation. And then I can simply use that new modified geometry in one of my simulations. Yeah. Now we have the internal flow volume. So that's represented by the blue color region, which can also be accessed at the right. So you see an additional part called flow region. So that is all I want. So I'm going to hide that. I'm not interested in the mechanical simulation at this point of time. So I'm going to delete all the other solid parts in my geometry. I'm left with my flow volume. I can save this as a new or a copy of my modified geometry. And at this point, all I need to do is go to the copied simulation template, swap the geometry to my new design. What SimScale does is if the geometry doesn't change too much, it actually tries to capture and associate all the conditions applied on the basic case to this new one. And that's what you see here in the simulation setup. After swapping the geometry, you get a swap report stating that, hey, one of your inlet is designed differently and that needs to be assigned to your boundary condition. But rest of all the assignments are preserved for your new model. So we go into the boundary condition. We say that the oxygen is being given through this particular phase, and that is all I need to do for a new simulation. I can save that, go ahead, start a simulation on the new design, right? I can wait for the simulation to finish, but since we are on cloud, you don't need to wait for these simulations to get completed to start a new one. Let's say I also have a flow rate condition that I need to check. So I go into one of the flow rate conditions. I see that it's already parametric. I want to add a few more flow rates to see how the flow looks like. So I'm adding and two more new flow rates to the oxygen inlet, and I can start a new experiment which has in total 6 different flow rates for oxygen, and I can leave them running in parallel, come back after some time, take a look at the results. This is how a designer can easily jump in, use an existing template, run a new simulation on a new design, and also get insights. In some scenarios, the work of a designer ends here. They can actually push this simulation to a simulation expert by sharing the entire project. So you can click on the private button, you can type in your expert's email ID, and then give them edit or copy access so that they can take a look at your setup and derive the results from that. Or you can share it with our support in case if you have any question on setting up the simulation. You can check this box, invite, and then you can also open up a chat sending us a message that, hey, I have set up a series of simulations. I wanted to quickly check if my simulation setup are valid or if I'm missing something. So one of our simulation experts can jump in directly into the project, take a look at your setup and guide you on specific points. Right? This is how the support works on a professional level within SimScale. Let's imagine we have waited for some time and the simulation is already completed. So it takes a few more minutes to complete, but we can jump into the template project and start taking a look at the results as well. I'll put on my expert's hat now. So I see that my designer has run a new design and I want to quickly check the results from the simulation, right? So I'm looking into the project where the simulations are done. I'm looking at second version of my mixer. And as a design engineer or a simulation expert, the first thing I would look is the flow behavior within the system. So we are within the post processor on this case, and I have a few cutting planes to show how the flow looks like within the static mixer. Here you can see the flow velocity varies quite a lot at the inlet, and we know that from the top, CO2 is coming in, and from the bottom, nitrogen is coming in. When you look at the inlet rate of nitrogen, it's about 34.8 liter per minute. And for CO2, it's 3.2 because of the less percentage of CO2 required. And this is one of the reasons why you can directly see a large recirculation bubble at the inlet of the CO2. This might be affecting the efficiency of the static mixer. So this is one design insight I can already see from the results directly. I can give this feedback to my designer to make changes on how the inlet actually looks like, change the radius of the fillet or maybe make a bend so that the gas comes in without any recirculation. Ultimately, what I need to check as a simulation expert is to see if the mixer is producing the gas mixing at a certain fraction of gases, which is required for the preservation of fresh fruits or meat, right? So to do that, I'm going to plot my entire geometry with mass fraction. And once when this loads, I can easily extract the flow fraction of CO2 or O2 or nitrogen at the particular location, right? Let's do that quickly. And then I can start collecting a series of data depending upon different flow rates that has already been done, and then start comparing whether my design changes are effective or not, and also find out the ranges in which I can give the flow rate for these gases to achieve the required gas mixing. Yeah. Yet once again, I'll remind the audience to use the question section, and we are happy to answer the questions. But quickly before that, we'll do that again. We go to the mass fraction, and now I will be able to see at a phase level. Let's say I want the cutting planes. I have all my components shown. I can select my outlet and see the average mass fraction component on that particular area, right? So this says that I have about 5% of CO2 coming out of this outlet. I can do that for my second component, nitrogen, and then do that for the third component as well, and then compare if this level of mixing is good enough for my particular product. These results can be extracted from all the simulations that you have done. I'm going to quickly show you how you can use the results right here. Right, put together a tabular column where you can see on the top we have the version 1 and a difference between 20 liter per minute flow rate and a 40 liter per minute, and the same for the second version at the bottom. And now I can see a clear comparison. When I compare it with the criteria that I want for the gas composition, all these flow rates of oxygen suits better. And then when it comes to the version 2, I see that at 40 liters per minute, we already achieve a lot of mixing, even with low flow rates of oxygen. So this will help you to devise the range of the flow rate for each gas. You can compare designs and find out the efficiencies, and also use one of the existing templates so your design engineers can quickly run these simulations, give it back to you, so you can focus completely on the product development rather than setting up the simulation from scratch. I think at this point I'll end the technical presentation, but we are happy to actually answer a few questions that we have from the audience. I'll invite Kanchan to join for the questions.
Yeah. Thank you so much, Ajit. I think it was a very thorough and step-by-step demonstration of not specifically only about the physics, but also like in general how the SimScale platform works. And I think our listeners viewers are definitely interested in knowing what the workflow is like, especially like if they're new to SimScale versus if they are seasoned simulation users. So we do have one question. We actually have uh, two questions. Yeah. So one is about the multi-component model itself, is whether this accounts for chemical reactions within amongst the gases, like any kind of mass transport. Do you want to take that, or should I?
Yeah, please go ahead. I think, yeah.
Yeah. So yeah, at the moment, no, it does not account for any chemical reactions. We are only looking at the transport of each gaseous species uh, by looking at the bulk flow properties which are governed by the Navier-Stokes equations, and then you solve an individual transport equation for each of the gaseous species. But there is no mass transfer happening right now. And we also don't account for chemical reactions, but possibly maybe sometime in the future, all of these things, we are rapidly developing our tool to include more and more comprehensive physics through, being able to solve more and more complex problems. So surely this is something that we can look into in the future as well. And there's an interesting question here about our AI features. I think that's about alluding to when I talked a little bit about AI in the introduction. So, does what exactly is the AI feature about in SimScale? Do you want to take that? Yeah.
Yeah, maybe I can start. Yeah. So SimScale has had AI in terms of predicting the runtimes and computational effects that is needed for simulation. But recently, with the AI prediction, you should be able to use all the simulations that you have already run to predict a new model. For example, in this static mixer, we have run about 15 or 16 different flow rates, 2 different geometries. Now that's a good training material already for AI, right? With SimScale, you can train the model using this simulation data. And then the next model that you want to bring in, you can actually swap the geometry just like what I did and start predicting the results instead of running the actual finite volume method or the simulation
Yeah.
itself. Yeah, I
So
hope that
you
answers the
can
question.
definitely, right, and you can definitely solve like run the full finite volume or any kind of solver, but typically what this does is that saves you time because it gives you narrows down the design space, and there's also a confidence meter that is provided within the workbench where how close the AI prediction is to the previous CFD result is shown to you. So the closer you are to 100%, the more confidence you will have that, okay, yeah, AI is giving me the right answer. And then based on that, you can zero down on, the final designs that you want to work on. And then of course you can, do more things and run the full-fledged physics-based simulation on those particular models. There is a question specifically about the mixing model that you presented, Ajit, is if you can analyze the mixing at any point along the mixer and not just at the outlet.
And that's a good question. So in the setup, you can definitely ask for probe points. So in the result control item, instead of looking that at the outlet or inlet, you can keep probe points just like what I did at several intervals of the gas mixer. And then as a result, you should be able to actually see how the mixing is happening. Let's see one of the components here that it's going to write out all your mixing efficiency or the fraction of mixture at each and every point within your domain. So that's possible. Yeah.
Thank you. And also there is a question whether there is a tutorial available for the multi-component model. We do have documentation for the multi-component model on our website, and as a follow-up, we can share all of that information with you guys, and we can also make this particular simulation itself available to you as a tutorial. And in general, like if you want to know about the different modules, different solvers within SimScale, for sure, there are many other tutorials. You just need to go to, I can share. I'll actually post the link to our tutorials and validations in the chat option for you.
Thanks, Anton.
One more question about design of experiment, and I don't know how much time we have. Nagman, please alert us if you're running out of time, but I'll take this one. Is there any option to create a design of experiment where you can handle all the treatments in the same place and observe the system response? I can start off answering this question, Ajit, but please help me out if I don't get it right. So currently within the SimScale platform, you can create a design of experiments. So you can launch a DOE by varying non-geometric parameters. Like say you want to see what the response would be at different flow rates. So you can just give that as a tabular input, and here you see up to 6. You can give like hundreds of those simulations, and all of them will be launched as an experiment, and you will get like collated in data on how like the area averages or how all of these different data points behave at a particular point. So that is what is possible within SimScale. Some of the parameters that you can uh, make a part of your DOE are inlet and outlet pressures, RPMs, flow rates, velocity inlets and outlets. And by leveraging our open API based our API, you can also link SimScale to your native CAD package to enable a geometric design of experiment as well. So I can give you an example of a case study that we previously did with cases. It's just one case study. As an example, I'm sharing this with you, where we were able to do a shape optimization for a valve by connecting these two tools, SimScale and cases, through the API, and ran about about 900 simulations in 1.5 days, like literally about 42 hours. So there were about 14 constraints on the shape of the valve, and the objective was to optimize the flow rate, the CV value through the valve, and that's the simulation lead times that you're looking at. So that's what is possible right now. In future, maybe in the next 1 year or slightly longer term future, we are also working on implementing these kind of geometric design optimizations, geometric design variations and DOEs to be possible from within SimScale as well. So yeah, stay tuned for those updates. I think we have answered most of the questions. So if nothing else, I think this has been a good talk, and it has been really nice having you all as our audience. And I hope there was some takeaway for all of you through this presentation about SimScale, about the applicability of SimScale for the food processing and manufacturing industry. And as engineers and experts and students yourself, we would love to hear from you. Our emails are available to you as when you get a follow-up for this webinar. Please feel free to reach out. And if you would like to access the multipurpose solver, specifically the multi-component model, please get in touch with our sales team or just simply respond to the email that you got from our marketing team as well. And someone will get in touch with you to set up a one-on-one demo as well. Another way to also start, if you're not sure whether you want to a personalized demo, just go on to simscale.com, create an account, and start using the platform. But I must warn you that the free version has limitations on the number of features that you have access to, but it definitely is a very good way to get started and get a feel for the tool itself. So that's it from us. And shortly in the chat, I will just share the link to our tutorials as well. So thank you everyone for joining. It's been wonderful presenting to you all. Thanks, Ajit.
Thanks, Kanchan, and thanks everyone for joining. We'll see you in the next one.